Our first speaker is Dr. Seid Koric, who is the technical director at the National Center for Supercomputing Applications and a research professor in the Mechanical Science Engineering Department at the University of Illinois Urbana-Champaign. Dr. Koric was leading research projects on the pentascale high-performance computing system of Blue Waters that demonstrated the scalability of engineering industrial applications. His expertise spreads wide, covering multiphysics, advanced manufacturing processes, sparse linear solvers, biomechanics, finite element methods, artificial intelligence, and also industrial high-performance computing. So welcome, and you may want to start your presentation.
Great, thank you, Zongrid. A nice introduction, and always good to be here. It's great pleasure to be here virtually with all of you guys, and especially give the talk in this research group and Professor Koric, who I believe is the #1 leader in this young research in the confluence of artificial intelligence and classical numerical methods. This confluence way, that's how we actually coined at the University of Illinois. But then, there are some people who are actually embracing that. We actually recently wrote a proposal. The Professor Koric was, supporting us to NSF to give us more HPC resources, especially, designed for this kind of applications. And we call it actually a confluence of AI and classical numerical methods. Okay, so let me start. Just briefly about NCSA for people who are not familiar with, we are one of the largest supercomputing centers here in at least on this side of the pond, the American side of the pond. We open our doors in '86. We host some of the most advanced open science cyber infrastructure in US. And what is important, actually, machine come and go, but we have people who are provide really expert support, expertise, and consulting for both academic and also for industrial research communities. NCSA is known for Mosaic, which was actually first successful web browser, started in '93, long before my time. Then, first Linux cluster Ethereum based was actually comes online here in 2001. And then all of these big, projects, what NSF actually funded, like TerraGrid and Exceed, that gave access to open science researchers in United States, were actually hosted here. We deployed and supported the first sustained petascale system, open science system of Blue Waters, which actually stopped working. We decommissioned it 2 years ago. And we also have oldest and largest industrial supercomputing program in the world, and also 1/3 of Fortune 100 companies actually did work with us in the past.
Seid, I have a comment to make here.
Yeah.
On the Mosaic, I use the browser Mosaic. I'm the only one maybe in this audience that have used it. And not only that, I was a panelist of NCSA at the time, and in the NSF panel, and Larry Smart gave me a T-shirt. So I have a T-shirt that says Mosaic. So if you want, I can sell it to you. Or
Thanks, George. Depending, how much you're going to charge me, right? Thank you. Yeah, Mosaic was a really big thing, and then that's how actually the whole business with internet started. Before that was a little black and white typing, apparently. That again, it was before my time at NCSA.
George, this is so cool. Even I've used Mosaic at Northwestern '94, so it's really good.
Okay, so here at University of Illinois, I teach some of these numerical analysis classes, and lately I show them this landscape. I say we really historically went from the first paradigm, which was empirical science. People were observing things, then we started actually using governing equations. Quickly figure out, especially with PDEs, that closed solutions are limited. So we started using computers for numerical analysis, and then supercomputers, and then within last 20 years, more like last few years, we started confluencing using this fourth paradigm, which is more like a stochastic, big data driven approach to engineering and science. And I would give a couple of quotes here, and one is from Professor Andrew Yang, also, who is the founder of the Coursera. He said, AI is the new electricity. So if you think about, how electricity started, my old countryman, Nikola Tesla, when he came to this side of the pond, and he actually invented induction motor, and then, Edison invented, for example, many other things. And then, electricity started touching every facet of life, of people. And we believe, the AI is doing the same, it's just within a few years, it's going to be everywhere. And, it's amazing how quickly it's developing, not only in our confluence of AI in numerical analysis, but also in other parts of the life, So what Alexander Vilchko, for example, said, who is the chief scientist, Google says, what is a cutting edge? Now it's become commodity, in a few years. And when I look, when we started actually this journey with applying AI methods in numerical analysis, especially Dr. Diab Aboueda, who is here. So we actually started in 2019, and then, by now, some of these methods are already obsolete, but we are looking at the new things, and it's developing with a lightning speed. So I think everybody knows this, machine learning has been around for ages, and everybody knows about random forest, SVN, and all those things. But one characteristic with them is if you really have a large training data, you're going to end up with this red curve here, which is kind of traditional machine learning algorithms. The more data you throw at them, the accuracy pretty much is going to stay the same. But if we actually use neural networks, and especially deep neural networks, large neural networks, the accuracy is going to go up. But there's, like everything in life, there is no free lunch, and the price that you pay. This is one of our benchmarks, actually, that we come up in 2018, which was kind of wow, big stuff. That deep learning actually needs so much more computing power to actually be properly trained compared to random forest, but you can see the accuracy is really much better with deep learning. Good thing is actually now we have GPUs, we have TPUs, so we can really relatively efficiently train these neural networks nowadays. So this is another landscape. When it comes to confluence of convergence, some call it too, of AI, ML, and physics-based modeling. On the left-hand side, you have pure data-driven models with at least no physics from governing equations. On the right-hand side, you have the all physics, and then you have everything in between. And when it comes to history of all of these things, this confluence work also went to, like rest of AI, to a couple of AI winters. And then lately it's brightened again by the development of HPC, accelerators, GPUs, TPUs, and of course, all of these goodies that we have with the Python-based programming environments and open sources, MLDA libraries, sklearn, TensorFlow, PyTorch, JAX is great nowadays too. And then when it comes to, solving physics-based problems with ML, again, we can resort to data-driven, physics-informed, and lately, we started using deep operator neural networks that can be from both flavors. It can be data-driven and physics-informed. And what is in between is also very interesting. Once you actually start mixing some of the, let's say, observation, experimental data, but also some data produced from numerical analysis, you can actually end up with solving some ill-posed problems where there's a mixed physics and data. And probably the best example I know is what Professor Kandiarakis did with the flow over espresso coffee. There was some of these boundary conditions were not defined, but nevertheless, with this kind of machinery that we have, they were able actually to solve it. Okay, so going to the next one. So this kind of cartoon, what we do very often here on HPC, so we use actually HPC to generate our training data, at least for a data-driven approach. And you can see that, you know, we use HPC, both high throughput and parallel computing to you know, generate enough training data, and we don't we split, you know, we don't cheat really, you know, we set aside validation and testing data, and then we move to you know, GPUs, and on GPUs there is a less computational cost. What is important, actually, this thread that you see for the training of data, it can take quite a bit, especially if you are doing you know, tens of thousands of these samples. But you know, it's usually done once you do it, you know, just move to GPUs and train you know, the neural networks, and then magic can happen. You know, you can actually move those trainable weights and biases to a laptop, and you can see the happy guy here who can inference results instantly without modeling software or HPC. And industry especially interested in this kind of things. We have quite a bit successful with this approach. I'm going to show you a few examples. One is from topological optimization professor, Dr. Diaba Baida, who works with me. You know, we were actually able to publish few papers there in topological optimization where we really speed up these things. And one of them, actually, we were able to even, you know, design some of the new class of metamaterials there. I use this approach for sensitivity analysis, and I'm going to show you also through DeepONets, data-driven DeepONets, we are able actually to do quite a bit of work in heat transfer and plastic deformation as well. So I'm going to be mentioning plastic deformation often. I understand, you know, we have people from different backgrounds, not necessarily from engineering and especially computational mechanics. So quickly 101 about you know, the plastic deformation. So you know, when we actually do some you know, apply some external load to a body, we are looking at the displacements, and which are measure of deformation. Of course, you know, strains are even more important because they are sort of gradients of displacement. And then we look at the stress, which is a measure of material response to deformation. And you can see this, you know, string here, which is a typical example of elastic deformation, which goes back to original shape. And then when it comes to plastic deformation, like this deformation of the staple, it never goes to original shape. Actually, there is always some permanent deformation. Here you can see on the graph here. You know, if we go and you know, start yielding, there is a plastic and elastic deformation. But if we unload, or if you go to reverse load, there will be the plastic deformation still present all the time. And there is a nifty mathematics actually involved, how we do that, how we you know, integrate these constituent models in plasticity. And you know, it can go further with plastic deformation, which we call hardening, and we have isotropic hardening and the kinematic hardening. But you know, ultimately, if you come to something which is also viscoplastic deformation dependent, then you are, and especially in a thermal, you know, if you have a thermal loads as well, then you know, your material response becomes not only path dependent, but also time and temperature dependent. And it's, you can imagine, you know, when I did my PhD here at University of Illinois, well, gosh, you know, it's now 13 years or more. It's very hard to integrate those things, and I actually come up with a new method that later on Abacus implemented, and you know, it's a bounded Newton-Raphson method for local integration when you have these highly nonlinear phenomena that you have to integrate. But you can imagine it's even harder to predict that kind of behavior with you know, machine learning methods. And so this is the paper We published 2 years ago, I believe, in International Journal of Plasticity. So there was another group. I think Raisi and Bessa from Europe. They showed how the sequential deep learning method of RNN type, they can capture this strain rate independent behavior without Visco, with these LSTM, I think, basically. But we said let's make it even harder. So this is one of my projects where I'm actually estimating the viscoplastic behavior during the solidifying of the steel. So for the given thermal flux and taper profiles, which is, think about them as a time series, the DL model hopefully can be trained and then predict temperature and stress history, which can then be real-time modeling and even online controls of, for example, continuous casting and other steel making processes. So to make story short, for this one, turned out actually that temporal convolutional network, which is based on one-dimensional convolutional layers, which are sliding in a time, and they are, learn from current and previous time steps, and they are stacked, as you can see, on top of each other. And there is also the dilatation factor, which is increasing, and that's how it allows us actually to achieve larger septal field size. And what is nice with TCN is actually they don't have recurrent and data dependent calculations, so they can just capture the whole time series, and they are also very computationally memory efficient compared to, for example, GRUs and LSTMs. And we found out actually that LSTM really failed for this kind of problem. GRU was good, similar accuracy with TCN, but again, TCN was much more computationally efficient. So later on, some of my folks actually who are working in transformers, now they are saying transformers is the future, right? So they actually compare some of these long time series on transformers. They couldn't get any results. So in our opinion, when it comes to sequential learning, probably TCNs are the best choice that you can find. So this is what I was talking about. You can see the training time, and you can see the error, and LSTM basically failed. GRU was good, but much more computationally intensive, and TCN was accurate but also very computationally efficient. So here comes the major part. So if I actually do go through all of this trouble, and how quickly I can inference TCN compared to Abacus, for example, which was used to provide these solutions. So it turned out actually we were 1, 2, 3, almost more than 3, almost 4 orders of magnitude faster than finite element. And right now we are actually negotiating with some companies to apply some of these things to their online process controls. Another industrial case. At this one, they say it's actually their ROI that we created for them is millions of dollars, and I just wish, we saw 1 or 2% of that return, but we didn't, we just, we in academic world, we kind of go for SOWs, and, we just put the cost of your grad student or something like that, and turn out, you don't look at these big pictures. But what we did here is, this is actually sensitivity and uncertainty analysis of the optical iPhone assembly processes. And, when they are actually making these iPhones, people in, Foxconn, they put a bunch of lenses in a barrel. And, each of them, because of manufacturing, they have slightly different variable dimensions in microns. And then you can actually, based on these real dimensions and variations, you can actually do the finite element analysis here, and you can predict deformations through nonlinear finite element and contacts, and you can look at the particular radial and axial dimensions in some of these lenses after they're assembled. And then the question is, at least the engineers at Foxconn, they were asking, how these inputs are influencing outputs, especially if they are too deformed after assembly. They're going to change the geometry, and optics is going to be not so good, or even they may be actually under some kind of stress, too much stress. So they tried to do that classical way with the forward evaluations done by Abacus here, but turn out actually it takes forever even on HPC. So we proposed, we said, okay, why don't we train the neural network and then see, first of all, in some kind of DOE fashion, is trained neural networks going to be able to get the same results as Abacus? Turned out, the precision was incredibly well. And then, in this loop of sensitivity analysis and uncertainty quantification, we put the neural network, trained neural network, which is just doing, feed forward, which is very fast, fraction of seconds. So at the end, we opened their eyes. For the first time, they were able to see sensitivity analysis, uncertainty quantification, and they were able to tighten up some of these things on the input side, and apparently the whole process was improved, with the power of artificial intelligence. Okay, so then we, as I was talking to George, we have been quite a bit involved with physics-informed neural network, and they can be of what we call strong form, where we are using the PD, the governing equation itself, as the loss of the function. But we also invested quite a bit of time in what we call deep energy methods, where we are using some kind of energy, free form energy, functional actually, and try to minimize that one. And so this is the first example that we published in International Journal of Numerical Methods. We use DCN method, which is basically we put bunch of collocation points in the domain, and the 3D equilibrium PD is enforced on these collocation points. Of course, this is spin, so no data is generated. We look at the different constitutive models, started with the simplest one, linear elasticity, hyperelasticity, plasticity, sampling. FEA solution was used only for pins validation. You can see some of the hyperparameters there, and that was back in I think it was 2021, maybe not 2022. It was one of the first, if not the first, pins application in 3D solid mechanics. You can see probably the hardest one was the plasticity, again because of the path dependency of the load. And you can see the two loops here. One is where we actually were enforcing boundary conditions and PDE, equilibrium PDE, through the constitutive equations on the collocation level. But then you can do that in one shot, one time increment, quasi time increment. But then we use the transfer learning between the these time increments. Just to give you an idea, in classical numerical analysis, we are using Newton-Raphson method to march in quasi-static time. In this case, actually, instead of that, we use transfer learning between those steps. And you can see some of the results with the DC.
Sorry, Seid, can I interrupt you for a second?
Sure.
Do you mind going back to the previous slide? This is Nat Trask at Sandia. Can you share a little bit more about the radial return algorithm? There's a lot of people who are interested in using pin as a stepping stone in order to actually learn like a plasticity response or yield surface or whatever else. Is there anything in here? It's hard to just like look at the pseudocode and parse it out. Is there any insight that you guys found or wisdom that you can share about what went into getting the radial return algorithm to work?
So radial return algorithm was used just to do the constitutive equation, the integration of the constitutive equation in each of these collocation points. It was a classical, radial return algorithm. So we didn't tweak that one at all. It was just, based on displacement that we are getting from neural network. We did some automatic differentiation to get the strains, and then we would proceed with the classical integration of the using radial return algorithm.
So like out of the box classical, and there's no issues with discontinuities and automatic differentiation.
Oh, there. If I go here, so to be honest with you, we had to use Diab is here. He can probably Diab, are you here? We don't hear you. I think you are here. Anyhow, so we ended up actually with an enormous amount of collocation points in order to enforce the proper accuracy for plastic response, and that was one of the minuses here for sure. But then we moved to deep energy method with plasticity, and here we are using free form, functional we can get it from virtual work, for example, and so we use the total free energy as a DM's loss. Only first order differentiation is needed. Remember, if you go back to DCN, in order to enforce the governing equations, there is a first derivation which is going from getting the gradients of the stress, but then stress itself is actually based on strains which are gradients of displacement. So basically you are talking about differentiating twice the displacements which are coming here. In this case, since we are using the free energy functional, we just have to do that once. And on the minus side, remember before we had a collocation point. Now you have to some kind of elements in order to actually do some integration on those little pieces, which we call elements, which you can call them elements. And then what we ended up here was generally more smooth and accurate solution than DCN. And again, transfer learning between the load steps was enabled. Jimmy, are you here too?
Yeah, I am. Yeah.
So Jimmy did this work actually very recently, and we published again in the International Journal of Plasticity. Jimmy, maybe you can say a few words about the transfer learning that we did between the coarse mesh and the finer mesh. That's how we actually that was the only occasion we were able to beat the finite element, right?
Yeah. So and on top of that, I kind of want to connect back to the previous slide that Dr. Koric showed about the very fine mesh. This one ended up having 1.2 times 10 to the 11th nodes in this cubic domain, and in the next one. So Dr. Koric, can you So in this one we use 100 by 100 mesh. So same neural network architecture, just on a very coarse mesh. We do a comparison just between the deep energy method and the collocation method on the same neural network architecture. This one, we were able to train the energy-based method in like 48 seconds. The collocation method taking more than 1,000 seconds, and we still achieve a much higher accuracy when the neural network architecture and the mesh is the same. And we can achieve convergence and a very accurate result even with very coarse mesh here. Yeah. And regarding the inference onto a finer mesh, we tried this example here on the left corner, the plate with a hole, we trained the neural network on coarse mesh, and then we were able to infer the solution directly onto a much more refined mesh. So we refined the mesh near the hole region where the stress concentration is expected. And then upon inferring onto the finest mesh, we were able to beat finite element by solving directly on the finest mesh. So yeah.
Yeah, thanks. And one more thing here, you can see physics informed neural network. So people actually started a long time ago to apply, neural networks even for the constitutive model integration. So, one way actually to speed up all of this would be we use again classical, radial return actually to do the constitutive equations. But there, we can put embedded neural network as well to do the inferencing for instead of integration, which can speed up further things. Okay, so we spend lots of time, but
hi, Dr. Seid, I have a question.
Uh-huh.
I'm Somdita from Brown. I wanted to know how many Gauss quadrature points did you use per element for computing the energy on when you use the DEM method?
Jimmy.
So those are reduced integration. We would do reduced integration for both the finite element and the neural network, because otherwise they'll just lock. Yeah.
But how many Gauss quadratures did you have per element?
Reduced integration, so one integration point.
Okay. Sorry, I missed that.
Yeah.
Thank you.
Okay. So
this is so cool.
The topic for folks was DeepONets. So finally we got to them, right? So we consider one of the
sorry to interrupt you. I'm just super interested in the details. So for the reduced quadrature, did you have to do like B-bar or something? Is there some stabilization that you need?
No. So those are small strain plasticity. So we don't have to deal with the incompressibility that much. So yeah, I guess those are only very simplified small strain J2 plasticity.
I think Jimmy put it on our GitHub already, this code. So you guys are welcome to explore further, right?
This is Suku here. I also have a follow-up to what Nat was asking. If you do your reduced integration, you'll get hourglass modes, right? Typically, because there'll be spurious modes which arise in the system. So typically with FEM, one has to stabilize them. So that's the main point of FEM when you do hourglass control, right? This work goes back to Belichko's work in the 80s, right? So that's what I think Nat was asking, that if you do under integration, you have to do some form of stabilization. Otherwise, if you do a matrix-based method, you'll get your matrix will not be invertible. So
again, to answer your concern, we actually really stay in a small strain regime, and we also, I think we also had quite a bit of mesh refinement here, that probably helped with some of those issues as well. But
I think it's not
it's a legitimate point what you're saying. No,
I think it's not an issue of small strain or large deformation. It's just, even if you do elasticity, for example, like linear elasticity with under integration, you'll have to stabilize it, because otherwise you can't.
Well, that's what Abacus does, right? Because they are offering.
Yeah, of course. So all the formulations are based on that.
Yeah, sure. Okay, well. Again, we really get pretty good results here, and you guys are welcome to check the code, and at least the comparison that we had here was pretty good with respect to even the difference between absolute difference between the finite element that we get from Abacus, I believe, and all of this here. Okay, so deep operator neural network. So what is really good with deep operator neural networks, it can learn the solution of the equation, but also the parameters. So, at least in our world of, computational mechanics, they can be loads, boundary conditions, source terms, even material properties. And, all of these networks that we had before, if you start actually changing some parameters, you have to usually retrain or do some transfer learning tricks. And it's really, when you look at the, neural DeepONets, they resemble classical numerical solvers, and, but they can inference results instantly. And when it comes to DeepONets, you can see that the basically two networks which are working together, and branch networks, it's getting parametric functions defined on M discrete points, which we call the input sensors, and the trunk network, they are getting output sensors. They can be time or some kind of coordinates on p random spatial coordinates, and then the scalar product is happening where we are merging those things. And usually, if you have n samples for parametric functions and p of these every time, so the scalar multiplication is happening, dot product is happening n times p times. But usually what we do, we have some kind of batch size. You go through these iterations with the batch size before the entire, the number of n times p's is used, and then the new epoch starts. And every time, at least for the data-driven part, we are comparing with the corresponding targets, and just like any other neural network, the weights and biases, they are updated, through the backward, passes. So this is equivalent of the physics-informed DeepONets. Like any other physics-informed, it trains without any data generations. The physics lost is informs on the Q interior collocation points, but we also have source terms or whatever is your parameter coming from these M points. So M points and Q points, they don't have to be on the same locations. If they are not, then you use some kind of trick with the interpolation between them. Training time, obviously, because we have to enforce the in this case, for example, you can see the Poisson's equation longer than data-driven, and often longer than even FEA. So in that particular paper that I was talking about, it was published recently. So we solved the Poisson's equation 2D on a square, but it can be done on any shape you want. I'm going to show you in the next example, that we are actually working with complex shapes as well. A little bit about Poisson's equation. It's elliptical, but it has this non-homogeneous part, which is source. So for us in mechanical engineering, this is a heat conduction equation with the heat source. And Poisson's equation or heat conduction equation is ubiquitous, obviously in conduction, in CFD, if you have pressure solver and coupling, in gravity, in molecular dynamics, electrostatics. And what is happening in all of these codes is that Poisson's equation with the with source is solved repeatedly with the same boundary conditions but different sources. And of course, I show you examples where can be used in sensitivity optimization, designs, uncertainty quantification. Like any DeepONet, it's a perfect candidate actually if you are browsing through some kind of space of parameters. So these are some of the results with targets versus prediction on that square that I was mentioning. So on the left-hand side, you see the pretty arbitrary, distribution of the source term, and then you can see the numerical solutions obtained by finite difference method. We use both, explicit Jacobian, implicit with matrices in all of that, and then you can see how well we predicted all of these things. Numerical solution was again obtained on 121 times 21 grid, for number of samples, number of sources, we use about 5,000. We vary this number of output sensors. In this particular case, it's a 400. And so nice thing about Poisson's equation is actually smoothing out the solution. So you can see it's the nature of the beast. It's a diffusive solution. So you can see how actually transferred to a solution, which was a relatively easy task for DeepONet actually to predict those. If you have something different where you are predicting not so smooth solutions, then DeepONet may have some problems, but we are working on a solution on that as well, just to be honest with you guys. So this is a little bit of the L2 norm that we compared with different parameters. So obviously, as we engage more of the sample functions for the source, the error went down all the way to 3% or less. And then the other thing is actually how many number of those output sensors we are randomly using collocations. And one thing is if you increase them, your accuracy is going to go up as well. So this was actually among the 250 something like that testing samples never seen by the DeepONet. And then when it comes to other hyperparameters, you can see, for example, as we were increasing the number of neurons per hidden layer, going from 25 to 100, it went down. And then also the number of, hidden layers itself, it also went down. But of course, training time went a little bit up. And this was on, I believe, older generation that we have V100. On A100 even less than this, talking about 10 minutes maybe to train this. Again, very important part is, how well, when you actually train all of this DeepONet, how well you are inferencing. You can see, FED Jacobi takes few seconds to solve this. FED implicit, which was using very optimized Python, libraries, it went about half second, but that DeepONet was 10 to the -4 or something like that. Again, 3 or 4 times, 3 or 4 magnitude faster. So what one would say, that what's the point? I can solve this so efficiently with classical. Well, the problem is actually if you start scaling, if you go to larger problems, if you are using dense factorization, it's going to be O to the n3. If you even with sparse factorization, it's going to go to the quadratic. So if you're talking about really big problems of millions of these, which people have with these variable heat sources, then our cost of inferencing is going to be really small. Again, maybe 10 to the -2 or something. So there you go right away, how you can actually speed up all of these things. I was mentioning we did physics informed versus data driven. You can see the correspondence was pretty good, but then we did a little bit of further investigation there. So you can see on the left hand side mean of the relative L2 error for again maybe 200 testing or 500 testing samples. And you can see, I was mentioning, if for the physics-informed neural network, those collocations points are coincident, they are on the same places as those input parameters, where we are defining them for the heat source, and then there's no interpolations. Obviously, when Q is on M, the blue columns, you can see they are more precise than the green ones where we do some interpolation. But what we have discovered also is that data-driven DeepONets were more accurate than physics-informed neural networks. One reason is, of course, when you do physics-informed neural networks, you know, you have to go through automatic differentiation actually to get to those terms, you know, for the PDs. Probably some precision is lost there. Why, you know, for data-driven, you know, something like Abacus or, you know, FED actually did the job for you. When it comes to training time, you know, physics-informed obviously takes much more time than the data-driven. But of course, you know, data-driven takes lots of time for, you know, generating of the data, right? Okay, so another problem now, you know, we were really encouraged. We said, okay, you know, we can solve the, you know, Poisson's equation. How about plastic deformation? So this is the one which is in revision right now in engineering with computers. How are we doing with the time? Some time. So this one, we use DeepONets actually with a bunch of parameters. So, you know, DeepONets with these 6 parameters, which are on this square, they are the magnitudes of the forces, loads. So you can see we are changing the force load in some range, but we are also changing the signs of those loads. So they can go to compression and tension, they can go to upward bending or down bending. We are also changing the material properties, namely elastic modulus and plastic yielding. And we were interested, you know, can DeepONet with this kind of parameters, which is basically serving as a surrogate to one Mises stress solution, and it's parameterized basically by these discrete values of loading condition material properties. Can we get the solution, you know, if we train it properly? Turned out actually most of the cases we really get a good solution up to 2-3% L2 norm error. Again, we look at the compare the inferencing of this kind of DeepONet with the you know, finite element with Abacus. Abacus, by the way, is very optimized. It has a parallel processing too. So we found actually the about 3 or 4 orders faster than nonlinear FEA for the new loads and new material properties. But what is very important here, guys, is you know, we don't need any retraining or transfer learning. You know, we just present the new sets of these 6 parameters. We can get boom instantly results with the DeepONets. And then we dig a little bit further. As I mentioned, plastic deformation is actually path dependent. So if I put some kind of amplitude here, changing this load in quasi time, you know, every time when I change this amplitude randomly, you know, I'm going to end up with different kind of plastic deformation, different kind of one Mises stresses. So we actually did that test too. And we ended up with having really good prediction on the small level. And we actually use one of the reviewer in this paper. You know, he said, you know, can you guys do you know, more complex geometry? So we actually use this big dog bone, and then we actually went and did a little bit more, you know, more extreme load amplitude. We started actually losing precision at the end, you know. So some work is probably needed if we go into combined geometric nonlinearities and with you know, material nonlinearities, especially with this path dependent loads, changing, you know, number of significantly changing actually number of samples, number of points inside. We were even thinking about, you know, remember the branch network. So maybe, you know, since all of these are dependent, right? Loads are dependent. We can actually maybe use TCN in you know, in a branch neural network instead of, you know, MLP that we have right now. And this is actually, Jimmy can say a few words about this. This is our last slide. So this is the one where we got inspired by the recent work here from Brown University in microstructure evolution. So we thought we can use the same approach with the topological topological optimization. And Jimmy, you can say a few words, what we are trying to do here, if you are still here.
Yeah. So in this work, we're trying to basically accomplish two different things. So the first thing is to use a DeepONet to sort of evolve the design into topology optimization under a particular node. And the second application is to sort of predict the stress distribution given a certain input design. So in a way, basically switching very complex geometries as inputs of the DeepONet and predict the stress field on these very complicated geometries. So that would be sort of like a step forward towards what we previously did on just a square domain with plasticity. And now we start considering not just a square domain, but actual complicated geometry that's inside of it. Thank you.
Thank you, Jimmy. So many people got involved, obviously, Dr. Dia Baboida, who has been from the beginning, working with me on this. Jimmy, you just heard from him. Amazing, bright talent. We have collaborators from Khalifa University, Asha Viswanta, person who worked with me on the uncertainty quantification. He was our postdoc. He moved to Google. Lots of faculty members you can see from different places. NCC Research Consulting Directorate, Industry Program, Foxconn, that actually funded that work with uncertainty quantification. We recently got a CSSI grant at National Science Foundation to do some of the, cyber infrastructure for this kind of research. We also have AI Center for Excellence, Center for Network Intelligent Components, and then, of course, you don't see it here, but Crunch Group at Brown University. Always, we were inspired with your work and looking forward, especially on the one that in progress right now, to work with you, maybe, to apply the concept that you do in Microsoft Evolution, actually in a topological optimization as well. So with that, I'm coming to end of this talk now. I'm sorry, I was envisioning to leave at least 10-15 minutes, for Q&A. It looks like it's less, but I'm opening for the questions and answers.
Thank you, Professor. No. Is there any question from the audience?
Sorry. Yeah. Hi, this is Martin Max at Brown. I was just wondering if you had been applying plasticity to deformable, where the domain is changing in time. Whether you're using Lagrangian material coordinates.
So we were that's a very good question. So we were talking about, if we can change the boundary conditions, if we can change the loads, if we can change even the material properties, can we also change the the geometry as well? And one thing maybe to start is from here, where you can actually do some kind of encoder to encode different geometries. And this one particularly, I think the CNN based autoencoder was used to encode the geometry. Actually, geometry is more like well, it's changing. So yeah, so it's a work in progress. I don't know if anybody has from the audience other experience. Have you been able to encode geometry? I know, for example, in this paper with from Brown University, maybe some of those people are on the call too, you know, they can talk more about, you know, we just started with this, how the, you know, geometry of the, you know, those microstructures were encoded into all of this.
Seid, I want to mention a couple of papers. I don't know if you've seen it recently. One is by some data, actually, and Johns Hopkins collaborators on DeepONet for transfer learning, where you learn in one geometry, you can transfer to another geometry. And that that was published in Nature Machine Intelligence recently. That's an important work, in my opinion, because it shows that it's not enough to, when you transfer learning, to just penalize the regression. There's another loss that you have to include, and that is the conditional shift in the distribution. So you have to penalize that, otherwise you don't get. So that will go from different geometries, actually. From one geometry, you learn to one geometry, you transfer to another. Another paper is by Lulu's group now at UPenn on reliable extrapolation of DeepONet. There's like, I don't know, 1 dozen or 16 cases, I think, that we also have there for going outside the distribution in shape, in parameters, and so on. These are all very detailed studies. So I just want to bring those to your attention.
Okay, great. Yeah, to everybody else too, right? Because that was the question. Exactly. Yeah, yeah. Any other questions? Jimmy, do you have questions for brown people here? You know, I think you had some questions quickly. I think you have one minute with this implementation.
Yeah, I think I'm good for now. Yeah, thank you.
Okay.
Great, thank you. Thank you for your presentation.
Well,
yeah.
thanks everybody, guys, and you know, looking forward to collaborations on this very interesting area. You know, yeah. Many people don't believe in this, you know, but we surely do, and you know, I think we're gonna see lots of this in the future.
Thank you. Thanks, Seid.
Yeah.
All right, so we move to our second talk. Our second speaker is Professor Daniele Mortari from Texas A&M University. Professor Mortari has been a professor of aerospace engineering at Texas A&M since 2002. He received his doctorate degree in nuclear engineering in 1981 from University of Rome. He's currently the editor-in-chief of the functional interpolation section of the Journal of Mathematics. During the past few years, his research has focused on orientation and positioning and position estimation of the spacecraft's additive sensor data processing, satellite constellation, and various topics in linear algebra and numerical algorithms, including function inversion, functional interpolation, differential equations, rotation in n-dimensional space, etc. Professor, are you here?
Yes, I am here.
Oh, yeah, I see you. Yeah, you may want to start the presentation.
Okay, thank you. I would like to share the screen. I don't know how to do it here.
There's a button on the
bar.
Oh,
here we are. Okay. Okay, share the screen. Okay, you see the screen, right?
Yes.
Okay, I will put it in the view. Okay, so this is a relatively new research because it started on 2017 and is basically the extension of a concept of interpolation. So I will show you what is the current status and what are the applications, the main application of this. Okay, first of all, what does it mean functional interpolation? Because it's not, it's a new concept actually. And so we will see, by the way, you see my mouse here?
Yeah, we can see that.
Okay, so I need to use this one.
Sure.
So we will start with the univariate. Okay, we will see what does it mean, this G of X. Okay, first of all, let's start with the beginning, with a very simple case. What does it mean performing function interpolation using just a single point on a plane? Usually interpolation is selecting a class of function like a polynomial, in this case line, that pass through that point. So what function interpolation wants is to write down an expression which is not a function, but a functional, that include all possible function passing through that points. And this means also discontinuous function, also even partially defined function. And this has been done with three different approach, which is the additive approach, rational approach, and the linear approach. The linear approach open up all what I'm going to present. In this case, the linear approach is almost trivial, is this one. So you see that the functional basically, the constraint is to pass through the points of coordinate x1 and y1. And so when g of x can be any kind of a function that is defined at x1, because otherwise you have some things that is undeterminate. And but that is the only constraint, so which is not basically is not really a constraint, because you want to pass through x1, and so you cannot include a function that is not defined on x1. So g of x can be any function, so that when x is equal to x1, they cancel and so on. This is very simple. Now the theory increased, and we found out the general story of this, which is by including n constraints. And n constraints means basically point, derivative of any order, integral, limits, any linear combination of them. And this has been done by two equivalent formulations. So g of x is still a function that must be free. And as you choose this free function, you are spanning all possible functions, simultaneously satisfying all the constraints. In the first formulation, these eta k are some coefficient functional, and the sk are support function. So this is basically the same function that you use to doing the interpolation. The other equivalent function that is a little bit more difficult to accept at the beginning is basically made a product of a switching function and projection functional. But we will see later what does it mean, these two. To give you an example, imagine that you are looking for to describe all possible function where you know the second derivative at -1, so this is assigned, that the function pass at the point 0, assigned at 2, but at 2 you know also the derivative. So you apply one of these two formulations using monomial as a support function, and you obtain this equation here. This equation represents all possible functions that simultaneously satisfy all four. If you put g of x equal to 0, you are doing just a simple interpolation. Okay, you can imagine. You can
Daniele, can I ask a question?
Sure.
Suku here. So when you choose s as 1x, x squared, x cubed, then is it possible that, do you know for sure you'll get a solution? Is it invertible, the matrix, or?
Yeah, I will talk about this a little in a little bit. Okay, the only important is that this support function must be linearly independent. Okay.
Yeah, sure. Even if they are linearly independent, is it always guaranteed to give you a solution?
No, it's not guaranteed because it's the same problem for interpolation. Suppose that you have only this constraint, right? The first constraint, the second derivative, and you use one super function, which is 1.
Yes.
You are killing everything.
Exactly.
And so the problem is not something different in the functional interpolation. It's the same identical problem that you have in interpolation in general.
Okay, thanks.
Okay, so here you can see, for instance, the effect of the switching function. Switching function basically are a function that becomes 1 or 0 when the corresponding constraints are verified. For instance, the second constraint is verified at x equal to 0. So when x is equal to 0, basically this is 0, this is 0, this is 0, and this is 1, and this is 1. So this is the switching function associated with this constraint here, and vice versa. So this is an example, for instance, where you want is an animation where you want to pass through these 2 points, and in addition you have a relative constraints that is at the 0 and 3. You don't know the value, but must be the same. And so here, by changing your free function, you are spanning all possible, and is an example, just all possible function passing through these points. Okay, oops. Okay, this is for integral constraint, for instance. I artificially change with the damped oscillatory behavior the boundary condition, and then I impose that the constraints must be, the integral of the solution must be constant. And so one of my students told me, Professor, you should put a fish in this plot, and I did it. Okay, so now why is important function interpolation? Because suppose that you have like solving differential equation, a constraint optimization problem. Usually you search the solution of your problem, your constraint optimization problem, in the whole function space, and then you try to enforce the constraint. When you write down this functional, you basically collapse all the whole function space to just the subspace that fully satisfy the constraints. And in this subspace, this is your solution. But the more important is that you are transforming a constraint optimization problem into an unconstrained optimization problem. And when you are able to do this, then you can solve a more simple, robust, accurate, fast, and a reliable method to solve it. This is an example, for instance, for a trajectory. So you have a 5 point in space that must be observed at the time T1, T2, T3, T4, T5. And this is basically the functional, which is a vector of a function, is a vector functional, and the free function is a vector of a free function. In this case, for x, you use a sine of a time, the exponential of t for y, and 1 minus t squared for zeta, and you obtain this kind of trajectory. But you can put here any kind of function, even 0 or discontinuous or partially defined or whatever. So this is, for instance, an example on how to solve, how to use the theory of functional connection to solve a boundary value problem on a differential equation. So this is a second order differential equation with the non-constant coefficient and is non-homogeneous. And it is subject to a boundary condition. So I forget my differential equation. I look only on my boundary condition, and I write the functional that always satisfies this boundary condition and containing the free function. So here you see also again the switching function. For instance, when x is equal to -1, this becomes 1 and this becomes 0, and vice versa when it is equal to 1. This is very easy. So when
Daniele,
you have this, yes, sir.
I have a comment on your equation here.
Sorry?
You know, one way to, well, I have a comment on the equation you show.
Yes.
Right. Yeah, you can view it as a convex combination of y0 and yf, right? Which is basically imposing the boundary conditions. And then you can look at another term, basically the gx minus the convex combination of the boundary values of g.
Yes,
so that's how one way.
this will be done. This kind of yes, you have a good eyes. So at this point, we have this expression for the solution. So we impose a solution like this, and we substitute in our differential equation, and we obtain a new differential equation that is a little bit more complex. And actually, this is a new animal in mathematics, because this is a new differential equation that is subject to no, it has a no, is not subject to any constraint. It has no constant of integration. It's like that you are bringing your constraint inside your differential equation, which is appearing with the G0, GF here and there. So since there is only one function satisfying this differential equation, because when you find out the expression of G, you substitute here and you have the solution. So you can express this free function as a linear combination of a basis, a set of basic function where xi is your vector of a coefficient. The derivative is this, the second derivative is this. And so you transform your differential equation, for which this kind of differential, we have no analytical approach to solve this differential equation. It's completely a new problem in general in mathematics. And so you transform this in a function that is depending on the independent variable and the vector of your coefficient. You discretize and you solve for xi, the vector xi by least squares. This is an example. For instance, you have a third order differential equation. You know the constraints is that you know that is a 0 at this value and at this value, and you know the derivative here. This problem has an analytical solution, which is this one. And I apply basically the TFC, and I compare also with the CHEP-FAN. I compare to CHEP-FAN trying to push at the maximum accuracy. And you see that basically a CHEP-FAN reach a mean or a maximum error about 10 to the -8, while TFC basically reach almost the machine error. Almost is a reach a machine error. And also on the vertical axis, you have the solution time. This has been done in MATLAB, basically, which is showing a 2 order of magnitude in speed and 8 order of magnitude in accuracy. Using the same differential equation, I try to make it more difficult the constraints by including an absolute constraints. So the function must be passed here. A relative constraints, I don't know the value at the extreme, but it must be identical. And integral constraints, such that my solution, the integral solution, which is the average, by the way, must be -1. I apply with I compare with the CHEP-FAN. CHEP-FAN is not able to solve, while TFC provide you the solution at the millisecond, which is machine error always level. This is for the residual. Then we know that you know, if you have a differential equation that has a behavior that is oscillating, you know, expanding the solution in terms of or even an orthogonal polynomial is not a good idea, because you face numerical trouble. But one beautiful aspect is to reach in a short amount of independent variable range the machine error accuracy. So in this Duffing oscillator that is chaotic, basically he has roughly a period of 4 seconds, roughly, because it's continuously changing this period. And so I decided to integrate only for one period, 4 seconds, and then use the final value that I obtain as initial value for the next period, for another 4 seconds. And I did this for 10,000 times. The problem is non-linear, and so it requires non-linear least squares. And so basically I solved it with only 2 iterations. And after 10,000 times 4 seconds, I obtain a maximum residual better than 10 to the minus 12. So this is the power of reaching the machine error level of accuracy. This is an example, for instance, of a 2-point boundary value problem in aerospace, which is my field, where you want to move from an orbit around Io and reach an orbit that is clockwise on the left side and counterclockwise on the right side around the moon. This is a complicated problem because it's not a 2-body problem and even not a 3-body problem. It's a 4-body problem because we include also the gravitational attraction of the sun. And you will see here, basically, this is a trajectory when they get close to the moon and they apply the second impulse. And so they start to orbiting around the moon in a clockwise and a counterclockwise, which is now basically. This has been applied also in the optimal problem, like in this case, optimal landing. So you have your own dynamic and you want to minimize basically the cost, which is your acceleration control, okay, the integral of your acceleration control. This is the approach is the indirect method. You write the Hamiltonian, you write down what is your optimal control, which is negative the co-state of relative to the radius. And you know that the indirect method brings you to 4 differential equations subject to a boundary constraints. So these boundary constraints are that you start from a given position and velocity, and you end up to another position with a given velocity. If it's a landing, you expect this r dot f equal to 0. And so you write down your constraint expression, which is what the function interpolation give you, and you write down your radius as a free vector in x, y, and zeta, and this is the product between the switching function and the functional projection. And so you have 4 constraints, and so you have 4 switching function, phi1, phi2, phi3, 4. The derivative, the co-state has a known constraint, and so this is just the free function. And so you can see here that you obtain in 0.4 millisecond the optimal solution with the position co-state loss, acceleration loss, everything at the machine error, and the Hamiltonian plus gamma also basic exactly 0, which is the definition of your optimality. Now, in this, for case of moon, we consider the gravity constant. More difficult is when you land on a small asteroid where the gravity is changing a lot while you are approaching the asteroid. To do this, we create 2 viewpoints where we impose the continuity in a position and velocity, and we split this in 3 parts, and we obtain still the machine error, the history of your acceleration and so on. So this is basically the end of my first part, which is about the ordinary differential equation. So the method, the TFC, provide the approximate analytical solution. So it's an approximate, but it's analytical. So this is good for subsequent analysis, like you need to do perform derivative, integral, and so on. The method unify the way to solve differential equation, because initial value problem, boundary value problem is just a subset of a multi-value problem, where you can solve your differential equation, putting your constraints everywhere, basically. Robustness is very low. I didn't have the time to show this, but the condition number is extremely low, which is indicated very good, very robust from a numerical point of view. Speed at millisecond, so really good time for real-time at application. Accuracy at machine error level, and constraint, basically absolute, relative, component, integral, infinite, and any integration of them. Inequality constraint is a special case. You cannot, is not there. Then we go to the bivariate. So how does it function? How does it work? The functional interpolation.
Professor Mortari, can I ask you a question?
Dr. Cardagnaglis, by the way, before you give me, I want to send you the greeting of Dr. Ragudas.
Oh, thank you very much. Yeah, for the aerospace department. This is really interesting, certainly for pins, and Mario, who worked with you, Mario Di Florio, has exploited. But I was wondering if there are any fundamental difference between what you're suggesting and what Pierre Lion suggested in 1996, which he called lifting. In finite elements we call lifting, but I think the French word was relevament, something like that. So it's doing something similar, especially with the switching, like the case of the switching function is really similar to what we use in finite elements.
Well, Dr. Cardinalis, I'm not aware about this. If you point me out this, I will, or better, since you know, you can see if there is a
I will send you the reference of Pierre Lyon's. It's actually it's a book, Mathematical Topics in Fluid Mechanics. He referred to that, but
you will see, since you are aware about this, you will see from my presentation if there is a overlapping with this, or there is something different. Okay.
Right. The inequalities. I mean, the question is the inequalities, because the equalities, I think, is similar. If there's anything on inequalities, or maybe in high dimensional space, I'm not sure, but there may at least the 1D case looks very, very similar.
Okay. Yeah. Well, there is many similar also with the spectral method, but also it's not exactly the same thing.
No, it's not like the tau method. Yeah, I know what you're talking about. The tau that Lanzos.
Yeah.
That's different. Yeah.
Okay, so now
can I ask a related question before you move to the next section? So yes. I just want to make sure I have my understanding correct. So at the core, the switching function is a Lagrange interpolant at the constraint points, which means in 1D, you're guaranteed, right, that you can always do that interpolation. In higher dimensions, that property doesn't hold, right? For an arbitrary point set,
we are going now to higher dimensions, so you will see what happens.
But is that the correct interpolation, right? Like the criteria for a switching function to exist
very
is
similar.
that you need a
work very similar. Let me go on, and you will see. Okay, so in 2 dimensions, we are the bivariate. Basically, our boundary becomes our points constraints becomes functions. For instance, in this case, are the Dirichlet constraints. So if you use your free function equal to 0, this is done by using a matrix. If you use a free function equal to 0, you obtain the simplest surface satisfying the boundary condition. If you use any kind different of a free function, in this case, this free function, you have a bumping surface, but it still satisfies all the constraints. Then on the theory, we develop for multiple constraints. In this case, you have 4 constraints in X and 3 constraints in Y, still with the G of X and Y equal to 0. And here I use a modular arithmetic, for instance, for the free function, thus obtaining a surface fully satisfying the constraints, but is discontinuous, okay? Because yes, the continuously discontinuity in X and in Y. Then we applied this technique to solve some simple and even a little bit more complex differential equations. And for this differential equation subject to these constraints, we obtain this residual and this error, okay? Now, I want to highlight that we applied this for using still the same identical approach. When you start to using a neural network, specifically, you know, the one explained by Mario, okay, then you can attack more complicated and higher dimensional PDE. Okay, no, now we go to the multivariate. So we generalize in n dimension. The generalization in n dimension is done, I cannot put all the theory here, we wrote a book about, is done using the tensor, where this C of X, in this C of X, there is the description of all your constraints that can be done, can be any kind of constraints. These vectors basically are the some vectors that are defined using the support functions, okay, and a matrix of a coefficient that it can be obtained just by inverting a matrix where these B are some special operators. This is connected with what the previous person asked me. If you look at this expression here, you can see the TFC doing something interesting, because this first part is basically what just interpolation is doing. So if you consider G of X equal to 0, now this second part, which I indicated with B of X, is all possible surface, all possible manifold. In this case, we are in n dimension, all possible manifold that are 0 at the constraint. So it's not disturbing the interpolation, but is changing all everything that is outside the interpolation area. So
Daniele, that was exactly what you said. My thinking was exactly what you were saying, right?
Okay, so yeah. I was expecting, yeah. Okay, so the generalization in n dimension has been done in 2 different approaches. This one is direct approach. You go and you write down these equations. How to write this tensor is on the book, and is a little bit more complicated. The second is is very simple to explain, because you use the unidimensional theory and by variable. So in this case, you have 2 constraints in X at 0 and 1, and 2 constraints in Y. Both of them are 0. In special case, these are relative constraints, for instance. And so you write down basically your constraint expression in X and Y. And what you obtain, for instance, in X becomes your free function in the Y in a sequence. And so in n dimension, this is basically performed by graph theory. You obtain exactly the same identical formulation, generalization of formulation. Okay. Now, very interesting is basically in n dimension, starting from 2 dimension on, what happens when you have constraints like a shear type or mixed derivative that is not appearance in my field, but I know in material, fluid dynamics, there is more in material, I think. So when you have, in this case, you have, you consider just an example. a square, a rectangle domain, and you have 4 shears, okay? So these are your constraints. Now you can substitute these constraints with the equivalent constraints that TFC can deal with. And by performing the antiderivative of these constraints. And so these are the antiderivative, and you introduce some constant of integration. Now, by enforcing the continuity, okay, you can your problem becomes a linear problem in your new constant of integration and your antiderivative, combination of antiderivative. This AX equal to B is not only enforcing the constraint. Now, if you look at this matrix has a rank 3. It means it's a singular. One row or one column can be expressed as a linear combination of the other. This means in order to admit solution for this problem, also the second part must be admitted the same identical linear combination. And so here you can write basically the general relationship in order for your constraints to be consistent. So basically this approach allows you to develop a general approach for shear type and mixed derivative where to find the consistency of these constraints is difficult, if not impossible. So we are able to transform this into a linear system. Now, TFC is developed for a rectangle domain, and we also developed it for triangle domain. This is just an example. And for more complex domain, physical domain, we try to apply the domain mapping. So this is your TFC domain, which is a rectangular. If you want to use complex mapping, you are able to extend to this kind of domain. Project mapping is much more promising because it allows you, by selecting some projection point, you can apply the TFC approach to this typical C-beam, I-beam, T-beam for structure, for instance. Another approach for physical domain is the polynomial mapping. And so you can apply the TFC to shape like this, or even more complicated. Now, I show you some application of this without writing equations because some of them require some time to be digested. So this application, inequality constraints. So the theory for continuous bound, for instance, allows you to describe all possible trajectory that remain inside the 2 boundary constraints. It is possible to combine inequality and equality constraints. And this is an example. For instance, you have your bound and you have some equality constraints here. And so you can describe this. Mixing the inequality with the limit or with the integral or derivative is something that we are not able to do it. Is still a subject of research. As for application, I've been working with the Jane Reddy, which is a very famous person in the finite element method. And we published 2 journal articles on linear and non-linear Timoshenko beam for a very simple beam in this case. And we obtain amazing result. So, and we are able to show that TFC is outperforming finite element method for very simple structure. I mean, in the realm of a microstructure. Obviously, TFC cannot be compared with the flexibility of the finite element method. And so it's not substituting for absolutely the finite element method, but it has amazing application
in the microstructure, where you have a simple structures like a plate or beams. Then we apply this in quadratic programming under equality constraints, find out a solution that is already existing, where our G is our free vectors. The important things here in this case, the equality can be written in this way, like a matrix by a vector equal to B. In general, this X naught is the pseudo-inverse, is a solution of the pseudo-inverse. In this case, you can use any kind of all possible solution of this equation here, which is an underdeterminate system. Then it has been applied also for nonlinear programming, still subject to nonlinear constraints, where you develop up to the second order your objective function. And we found out an expression providing you the solution as a number of iteration. And this is an example, for instance, of this. What I want to highlight in this example is that if you start, this is a nonlinear basically problem. And so if you start with an initial guess like 1, 0, and 0, this initial guess fully satisfies your constraint, okay? And by subsequent iteration, you see that the path of your solution follow always the path of fully satisfying your constraints. So you remain in the subspace that is fully satisfying your constraint. A professor from Vietnam has been able to prove, this is not made by me, that the method, he did the convergence analysis and he proved that he has a quadratic conversion rate and is a bounded number also of iteration, which is two very beautiful results for this. And as another application, just to show, this has been done on a curved space where basically the distance, the infinitesimal distance is provided. This is using Einstein summation, using the metric tensor, the covariant metric tensor Gij. Now, for the geodesic, the theory provide you exactly the equation where it appears some symbols here that are the Christoffel symbols containing the partial of your metric, the covariance metric tensor, but also the inverse, the contravariant metric tensor, which is nothing else than the inverse. And here, these are some example, for instance, applying this. You have 2 points, and the black is your initial guess, and is in an extremely fast way converging into the geodetic boundary value problem. This is for hyperbolic paraboloid, torus, and so also we tested also on the Moebius trees or a generic surface. Just to show you, for instance, a potential application, there's, for instance, in relativity, where usually the path of the light in a curved space-time is done because you know the initial velocity of the light, which is constant, and you know where is originated, the point. And then you integrate the geodesic equations, and you see the path of the path. In this case, if you want, you can solve a problem like where to shoot the light in order to reach a point, and following, you know, the path that the light is choosing, which is the geodesic. Then we apply this also the calculus of variation. So where you need to minimize a function, you minimize an integral, and this integral the argument is a function of a given function, which is the solution of our problem. And usually this function is subject to boundary constraints. So we know that this kind of problem is not completely sufficient, but you can transform in the Euler-Lagrange equation and transform this into I applied to the Brachistochrone problem, for instance, and we found out immediately the solution for the Brachistochrone problem. So transforming calculus of variation in a two-point boundary value problem. Then we applied also to homotopic continuation. Now, homotopic continuation is applied in a nonlinear optimal control, for instance, where you need to find the root of a nonlinear function, f of x. If you apply, I don't know, one of the methods, like a Newton method, it easily diverge, or it doesn't converge at all. And so the homotopic continuation introduces a different function where you know the solution. And you start with the t equal to 0, so that the resulting function h is coincident with the function you choose. And as you increase a little bit t and t, you converge in some cases to the solution you are looking for. There are different approaches to do this, but the TFC approach allows you to write down basically the same identical constraint expression using a free vectors, no, that can be expressed by a matrix of by vectors like this. So to show you an example of this, so suppose that the function, you know the solution is here. As you increase the t, the path of your solution brings you to the solution. This is what you desire. Unfortunately, in many cases, path appears like this. They bring you back, or goes to up infinite, or go to minus infinite, or they have some limit points. They can even go to the solution, but you have the limit points where you cannot increase t. There is some technique of a continuation here, but there you don't know if you are going back or if you are going to infinite at this point. So when we apply this, for instance, this work has been done, by the way, by a person at the Politecnico di Milano, Professor Toputo. So when you start, in this case, you have an homotopic continuation and you reach a limit point. At this point, you change completely your free function and you jump into another trajectory that allows you to continue. If you found another limit point, you change again the free function until you can proceed. And these are, for instance, two examples to solve one very simple example, and this is an application for nonlinear optimal control. This is also some step that we are doing in patching TFC solution. So you see here basically that enforcing the continuity in domains that are rectangular, that allows you to form any kind of domains. Application there is also in quantum mechanics, because in quantum mechanics there is a concept called the Feynman path integral, which generalizes the action principle of classic mechanics. So is a substitute a single trajectory with all possible, the infinite trajectory, connecting the wave function at the state A, at the time A, and the wave function at the B, at the time B. But the connection between A and B associated with the two different kind of time of the wave function can be written in using TFC, where basically your free function is a free wave function, basically, no, with free function. Okay, this must be investigated, how to sum all possible, because the Feynman path integral is the sum of all possible trajectories over this. So all the contribution given by all the trajectory. This is a sort of a last presentation where I can show you how TFC can be used as a mapping tool, where it allows you to, actually an interpolation in general, mapping object 1 in object 2. Let me show you 3 examples. First of all, mapping a rectangular matrix, 2 by 3 rectangular matrix, into a vector. So you introduce here 2 constraints. One, you look for a function whose argument is a 2 by 3 matrix. If it's this specific 2 by 3 matrix, you obtain this vector here. And this is a relative constraint where if you put this kind of a 2 by 3 matrix and or this kind, you obtain the same identical vector. Okay. And so again, here you can introduce support functions. Okay. And you can go to the support matrix, which is, this is the operator, is everything is in the book. So you compute and you obtain your constraint expression that allows you to describe all possible functions whose argument are this matrix, and they spit out the two-dimensional vectors and satisfying these constraints. So this is, for instance, mapping a vector space matrix. Yeah. This is an example for a finite field. So where you have a set of 4 elements, and you introduce 2 constraints. For instance, when you put the element 1, you obtain A, which is an element, and T is one of the elements of this. Whenever you want, you choose one of these is the T. And where the difference between FA and minus FT is exactly the T you want. So again, also here, you choose 2 linear independent support function. You go to the support matrix, you invert the operator of the support functions, and then you are able to write basically the constraint expression that works in the finite field and provide you this expression here. And there is also the possibility easy to verify that both of them are, if you use a G of 1 or G of A, you satisfy fully the constraints. Finite fields are characterized by addition table and multiplication table. And the last things, the mapping I want to show is something that I built just specifically for this presentation. So mapping a string to complex vectors. So if you put the word crunch, okay, the string crunch is spit out the vector 1i. And if you put f of a pin plus f of tpfc, you should obtain the same f of good. And so you use this support function, one is complex, and this is basically how to transform. So this is a constant, equivalent. So whatever string you put here, you obtain the same identical complex. In this case, you basically transform the string into a complex number. How? Well, X represent your, for instance, C, R, U, and X associated to A is 1, to B is 2, and so on. And so the real part is the sum of this, and the complex part, actually it's not the complex part, is a part of the complex part, is I elevated to the numerical value. So you still go through the support matrix, operator, and so on, and you can find the general expression that transform a string into complex and satisfy these 2 constraints. So this is basically, we reached the end of the presentation. I don't know if I am still on time. I think so. So I speed up. So there is a unit variable TFC that perform a functional interpolation. And this provide you is a generalization of interpolation. So provide you all function satisfying of linear constraints. And we have seen also these kind of constraints can be seen also as a mapping of different kind of object. What kind of constraints? Absolute, relative, component, integral, and so on. Then we extended the theory to multivariate, to n dimensions in a rectangular domain that can be you can find the constraint expression, your function that you're looking for in a tensor formulation or a recursive formulation. Then the domain mapping, if you have your physical domain is different, we analyze this. We can apply, so far to ODE, PDE, nonlinear probability, calculus of variation, of topic continuation, many other mathematical areas. An example to fields and so on. Not included in the presentation is the application of machine learning and TFC. I don't know anything about machine learning, and I don't want to know anything. I like what I know. You know, you are the master on this, especially in this first part in physics-informed neural network. Mario did an application, Mario and his group in Arizona with the extreme learning machine and TFC. We at the A&M, my students, they apply with the support vector machine of deep learning. Other things that I didn't present is the shear type and mixed derivative. How does it work with this? And also the general solution for the consistency of this boundary. Numerical TFC is where your constraints are described by matrices. Here is, for instance, the boundary of Italy. Okay, and so you have the boundary of Italy can be described by some value that can be positive, negative, and so on. And you want to describe all possible surfaces that satisfy these boundaries. Then this is the numerical. Hybrid system is when you connect different kind of differential equations. Okay, and so you can an example of hybrid system is a rocket. So when is on or off are two different differential equations. So there's the same differential equation, but sometimes disappears, and you have a sequence of these differential equations. These are the hybrid system. Theory of transition is something that is on my bucket, and I really want to dedicate my time of this and don't want to speak about because it's something really big that I'm doing. And I'm going to publish a couple of articles on the extension also to fraction operator. I know that also Dr. Kardaniakis did some application using pins there, I think, and then some more. As the resource, my two former students, they develop a toolbox in Python and everyone can download it. And recently it has been extended to complex and symbolic also. We wrote a book with my two students and is available in Lulu, Barnes & Noble's, Amazon. I am editor-in-chief of this function interpolation section in Journal Mathematics. We publish a lot. There is already 3 theses. Remember that this is pretty new, is just 5 years old. And I introduced a class in Texas A&M called optimization using functional interpolation. And these are the students I've been working with. We create the function interpolation with Dr. Karlik, now working at JPL, and Dr. Johnson at Aerospace Corporation, and we wrote the book. And these are, special thanks to all the people who give me an help. Most of them are professors in mathematics. And thank you.
Yeah, thank you, Professor.
So how to stop sharing?
Hey, it's all right.
Molto bene, professore Mortari.
Oh, bravo!
Grazie, grazie.
Chi è che, sei tu, George, che parli?
Poco.
Dove hai imparato?
No,
come
parlare
si dice?
italiano. No, non parlare italiano.
Ma tu conosci la frase italiani e greci, stessa faccia e stessa razza?
Yeah, una faccia.
Okay.
This is really interesting. There are lots of questions, I think, that I hear people. Nat, do you have more questions?
Yeah, I have a question. I'm trying to understand. There's a unisolvency question to all of this about the constraints, and I want to make sure I'm mapping this on correctly. So in some ways, for like Lagrange multiplier equality constrained regression,
Okay.
the switching function seems to be playing the role of a Lagrange multiplier.
Okay.
And there's a question, you know, if you were thinking of the KKT system, you would ask whether the Schur complement is invertible, right? If you're asking about whether you can impose these constraints. So it seems like there must be some property that the constraint that these switching functions have to have in order for this to be feasible, right? Like you need a non-empty set of feasible constraints, right?
Okay, so TFC is not doing what Lagrange multiplier is doing. So usually in a Lagrange multiplier, you can consider even a differential equation as a constraint, or an equation that is a function of a variable, for instance, a relationship between partials or whatever you want, okay? On TFC, these kind of constraints are additional differential equations that you need to add. So we cannot consider what Lagrange multiplier is considering as constraint. Okay.
So you don't view it in that, because maybe it's just superficial then. You have something that looks like, you know, usually you would have lambda transpose times the residual of a constraint. And it seems like a very similar functional form that you have with the switching function playing the role of, you know, goes where a Lagrange multiplier usually would go. So, so are you saying that's a superficial, there isn't a connection there between Lagrange multipliers?
Most likely there is, I mean, the theory is new. There is a lot of work to do, a lot of work of connecting the various approach, and I didn't solve everything. And, you know, it's, you know, I don't know how long, you know, the neural network are going. There is decades of study of several people. Here, basically, we have a very few person working on this in only 5 years. And it has been an adventure, believe me. And I don't have all solution of all this problem. This is a virgin material. And so, and I invite every one of you to work on this, to see connections, to see applications. And I think actually that the TFC is actually a killer element in a neural network, because neural network, as I understand, has some difficulty to impose constraints.
Yeah, of course.
Exactly. And while TFC is a killer application to impose constraints. And so this must be investigated much better.
It does give a new level of expressivity. I think that's mathematical and it's rigorous. So as you were talking, Daniele, I was thinking from many different applications in the PDE world where we need to impose constraints, and I'm not talking about controls. Even just like all the integral systems which have all these moments, so you know that in advance if you use them, but we don't usually impose those constraints. So that is just as a very simple academic example, but there are many others. But expressivity, I think that's the ability to express. So the fact that G of X is discontinuous that I think is tremendous. And I appreciate the last example where you were changing right at the point, the jump in the red line there, the g of x to make it discontinuous. That was really interesting to just to think how one, it gives you the possibilities.
Yeah. Okay, well, I remain available. So you,
Daniele, this was last remark from me. I enjoyed your talk a lot. And just to follow up on Nat's question, how do you choose the support function?
Well, you have the same identical problem of when you choose your function when you do interpolation. The same identical problem.
Yeah.
So instead of polynomials, you could use even sine functions, for example, or
Yeah. The only thing is you need to use a function that are linearly independent. By the way, I didn't say this. When you do optimization, also the free function must be independent from the support function that you've been using to derive the function.
Sure. Yeah. You can use radial basis. I'm sure radial basis would be good.
For instance. Okay.
Okay, thanks.
Okay, so again, I say I remain available for any kind of even potential collaboration in some papers.
Yeah, I want to talk to Mario, who started his job here yesterday, March 1st. So,
okay.
So I will talk to him and then we get back to you. Yeah.
Yeah, squeeze it, Mario.
Okay. Actually, Daniele, just to give you an idea how things are changing in the lab, Mario brought a bottle of limoncello. So
good.
Celebrate this afternoon for
crema di limoncello. We're going to drink it right now.
So Mario, is for everybody except for me, basically.
We're waiting for you, Daniele, to come to visit us at Brown.
Well, just invite me.
We will.
Okay.
And Daniele will bring the nocino.
Okay.
We want more Italians in the group. That's
I think this the generation is concluding my presentation, right? Okay.
Thank you very much again.
Thank you.
All right. If there's no question from the audience, thank you, Professor, for your lecture and presentation. So this is it for this week's Scrum seminar. Everyone has good Friday and weekend. See you next week. Bye.
Bye-bye.
Bye-bye.
Bye-bye.